In this example, we have a cogeneration cycle, which is essentially two cycles that are connected, in this case, by a heat exchanger. We've got a Rankine cycle that's using steam as a working fluid, our topping cycle, connected to a Rankine cycle using R134A as a working fluid, our bottoming cycle. Let's see. This entire system provides process heat through this heat exchanger on the R134A side, and we're told the superheated vapor enters the ideal steam turbine at 40 bar in 600 C. So here, turbine 1 is the steam turbine, and then turbine 2 will be the refrigerant turbine, if you will. Alright, so as we read this problem statement, we'll go through and fill in our pressures and temperatures that were given in the statement. So we know that pressure 1 is 40 bar, or 4 MPa, and that the temperature at 1 of that steam entering the turbine is 600 degrees C. And it expands to 2 bar, which is going to be the pressure at 2 and 3. And here in this heat exchanger, I'm allowing the steam to sort of wash over the pipes that's containing the R134A, but the two liquids are not, or the two fluids rather, are not going to mix. Okay, and let's see, this will also be the pressure at state 3. Alright, and then I've got an ideal pump that is going to push my saturated liquid at 3 back up to 4. So 4 is at the same pressure as 1. Okay, and we're told that the rate of heat transfer to the water passing through the steam generator, so this will be Qn, is equal to 14 megawatts. The bottoming cycle uses refrigerant R134A. The bottoming cycle is also ideal. So we have refrigerant entering the turbine at 16 bar and 100 C, so that'd be my pressure at A. And it's cooled in a heat exchanger that provides process heat and acts as a condenser. So we're now referring to this heat exchanger here. Saturated liquid exits the heat exchanger at 8 bar. So we know here at C we have 8 bar. And a saturated liquid. Okay, so the pressure at B must also be 8 bar. And the pressure at D will be the same as A. All right. So let's go back and work with our steam, and we'll define all of our enthalpies for our steam, and then we'll do the same for R134A. Okay, so at state 1 I have a pressure and a temperature, so it's just a matter of going through my tables to find where I have achieved both of these properties. And I'm going to find that, of course, as it states in the description of the problem, that I do have a superheated steam, and enthalpy comes right out of the table, 3674.9 kilojoules per kilogram, and entropy is 7.371 kilojoules per kilogram Kelvin. And because my turbine is ideal, I know that S2 is equal to S1. So I'll calculate H2 in just a moment. So saturated liquid at 0.2 MPa has an enthalpy of 504.7 kilojoules per kilogram. All right. And I know that my pump is ideal, so S4 is equal to S3. And I don't need to find these entropies outright, but knowing this allows me to say that H4 is approximately H3 plus V3 P4 minus P3. And you've seen how to look these properties up, like V3, and then convert pressures to, say, kilopascals. You've seen that in previous videos. So I'll save you the calculation and just give you the value at 508.7 kilojoules per kilogram. Okay, so now let's take a little look at H2. So I know that S2 is equal to S1, which is 7.371. So between 150 degrees C and 200 degrees C at 2 bar or 0.2 MPa, I can interpolate. So here's the enthalpy value at 150 degrees C. And I'm going to plug in the entropy value that I have, and then the entropy at 150 C. And that's going to equal the difference between the entropy, or the enthalpy at 200 minus that at 100. Divided by the difference in entropies at those two temperatures. And that gives me H2 of 2809.4. Okay. All right, so we can write that up here. All right, so now let's go to state A. So state A is a superheated vapor of R134A, and so directly from my table I can get the enthalpy value, 327.8, and the entropy value at A, 1.050 kilojoules per kilogram Kelvin. And I know that SB is going to equal SA. So for B, while we're on a roll, if I look in my R134A tables between 70 and 80 degrees C at 0.8 MPa, here I've got the enthalpy value at 70 degrees, the entropy value that I have at B minus entropy at 70 degrees, and then the enthalpy at 80 degrees minus the enthalpy at 70 degrees. And the difference in entropies between 80 and 70 degrees respectively, and that gives me H sub B now of 310.0. All right. So squeeze this in. It's 310.0 kilojoules per kilogram. Okay. So on to C. I know I've got a saturated liquid at 0.8 megapascals. So that's easily read from the table. 95.5 kilojoules per kilogram. And finally, I know that the entropy at D is equal to the entropy at C. So H sub D is approximately H sub C plus V sub C, P sub D minus P sub C. And that gives me an enthalpy value of 96.2 kilojoules per kilogram. All right, so now I've got enthalpy at every state. I can work on what's being asked in the problem statement, A through C. So A asked me for the mass flow rate of the steam. So I'm going to need to perform an energy balance on some component of the steam cycle. And so I'm going to need to know sort of everything about that component except for the mass flow rate. And the only candidate that I have is the steam generator. Okay. So when I draw a control volume around that, my only unknown is mass flow rate. So Q dot N is going to equal M dot H1 minus H4. And we'll call this M dot sub S for steam because we'll be dealing with another flow rate later on. All right. So M dot S is going to equal Q dot N over H1 minus H4. So I'm told I have 14 megawatts. I'm going to convert that to kilowatts. And that's because my enthalpy values are given in kilojoules per kilogram. So I have 4.42 kilograms per second. Okay. Part B asks me for the mass flow rate of the refrigerant. Okay. So I need to choose, again, one of the components in this refrigerant cycle, not refrigeration cycle, but refrigerant cycle. And the only unknown can be the mass flow rate of the refrigerant. And so the only candidate that I have is the heat exchanger. Okay. So I must find the mass flow rate of the steam first before I can perform an analysis about the heat exchanger. But since I've already done that, I'm good to go. So the energy entering with mass on the steam, so the net energy entering and leaving with the steam is going to be M dot S H2 minus H3, and that's going to equal what's coming in and leaving by refrigerant. So in these two cases, so I've got high and low, greater enthalpy, lesser enthalpy, greater enthalpy, lesser enthalpy. Right. H sub D. All right, so the mass flow rate of my refrigerant then, can be written and this gives me an absolutely staggering mass flow rate of 572.3 kilograms per second. And that's because of the extreme mismatch in the enthalpy values. Okay, and then so finally in part C, I'm asked for the thermal efficiency of the cycle. So, for a thermal efficiency, I need to look at my total net output divided by my heat input. So, here's my heat input, and my net output is going to be the output by both turbines minus the input to my pumps. Okay. I've got W dot cycle over Q dot N. And so I only have to take into account the heat entering my system. So the heat transfer that's happening between the two cycles is within the system, so I'm not concerned about that for the sake of thermal efficiency. So I've got output of my two turbines minus the work input to my two pumps all over Q dot N. So I can write this as M dot S H1 minus H2, that's turbine 1, M dot sub R is HA minus HB, that's turbine 2, minus M dot S, H4 minus H3, that's pump 1, and then M dot R, HD minus HC, pump 2, all over Q dot N, which I'm told is 14 megawatts. So I don't have to use enthalpies to calculate Q dot N because it's given in the statement. All right. So I will spare you the plugging and chugging here in this equation, but now we have all these values. And when we do, we get a staggeringly high efficiency of 97%. So is this realistic? Well, no. We're not going to be able to create a real-world cycle that has such an efficiency, but remember, we are in the land of hypotheticals here. We're also assuming that our cycles are ideal, and that wouldn't be the case either. So just take this value for what it is, nothing realistic, but at least it shows you how cogeneration cycles work.